All right, hello everyone. Welcome to the second to last session of the SBC conference. So my name is Mahdi Zamani. I'm the director of crypto research at Visa. So today in this session we have three talks. And the first talk, the session will be about the future of blockchains in general. We will start with Li Zhu from Imperial College London as the first talk. Somewhat surprisingly, this talk I think is not about the future of blockchains. It's mostly looking at the past to learn something about the future. And something also about the future. Li is going to be TAing a MOOC course on DeFi this year. The course is going to start next week. So if you're interested, he's going to show some information at the end of his talk about the course. So please sign up for that. Other than that, please allow me to welcome Li Zhu from Imperial College London. The stage is yours.
Thank you very much, Mahdi, for the very warm welcome. So, my name is Li. I'm from Imperial College London. Today, my talk is about quantifying blockchain extractable value, how dark is the forest. This is a joint work with Kaihua and Arthur. So many of you may have heard of the book Flash Boys from Michael Lewis. In this book, Michael has discussed a plethora of market manipulation techniques where the traders can adopt to kind of extract value from traditional market. So these market manipulation techniques in traditional market are typically regulated. In particular, in the US, we have the SEC, where the SEC come up with some rules where they forbid certain things from either individuals or companies. And they also enforce the execution of these rules. So in this particular example, we have a trader getting sued by doing spoofing manipulation. We also have seen companies paying fines, penalties to the SEC. In this example, it's paying 16 million USD. So what's interesting here is most of the market manipulation techniques in traditional finance can also be applied in DeFi. DeFi stands for decentralized finance. However, there's still no regulations in DeFi. So it's like a free zone, right? You can do whatever you want. We are not too sure what is legal or what is illegal at the moment. Okay, before I go into the details about MEV or BEV, I want to give a high-level overview on DeFi. So DeFi has a lot of services, which some of the services are mirroring traditional finance services. For example, we have exchanges, lending platforms, and etc. So these DeFi services build upon a distributed database with atomic settlement, which is also known as the blockchain. So atomic settlement here means I can have multiple financial actions in a single transaction, and either all the transactions execute successfully, or none of the transactions executes, so they fail collectively. DeFi also has some novel financial services, such as like flash loan and privacy mixers. I'm not gonna go into details about these services. But what's interesting here and what's also beautiful here is the DeFi services, they share some common token standards, like somehow they reached consensus. For example, we have the native token, right, which is Ether in Ethereum. You can use Ether to pay transaction fees. You also have fungible token, which is like ERC20, and you also have like non-fungible tokens. Because they are sharing this common asset standard, it means that you can have composability in DeFi, meaning that you can combine different DeFi services to create new services. For these financial services to kind of functioning efficiently and effectively, we also have market mechanisms. So two of the most relevant market mechanisms in this talk are the arbitrage and the liquidation. So in arbitrage, you have two exchanges. So the price of one exchange is higher than the other one. Then the arbitrager can step in and try to kind of balance the price so he profits from the yield between the two prices. The spread, sorry, from between the two prices. We also have the liquidation. In this case, simply the liquidator can purchase the collateral at a discounted price. Okay. So we had a high-level introduction of DeFi. But what is actually blockchain extractable value, right? So we frequently observe a common pattern where DeFi services, they rely on some market mechanisms, in this case, liquidation. And these market mechanisms leads to profitable opportunities. This is very similar to centralized finance or traditional finance. Think about home mortgage. Typically, the liquidation is triggered by a centralized bank. They can liquidate your house, right, if you can't pay your debt. What's interesting here in DeFi, because DeFi is a permissionless system, so really anyone can do the liquidation in DeFi. It can be a trader sitting in front of the laptop, triggering the liquidation manually. It can be a bot, right, detecting transaction messages and block states automatically on the P2P layer. It can also be a miner, right? Miner can actually censor the transaction from the other liquidators and also prioritize their own transactions. What's important here is who will be winning the liquidation, right? Who will be winning the BEV opportunities? In order to understand that, it's very important to understand the transaction ordering mechanisms in DeFi. Let's say in this case, we have 3 transactions, T1, T2, and T3. The miners may have received, for example, T2 after T3, but it may order T2 as the first transaction in the next block. Anyone knows why that's the case? I mean, it's because of transaction fees. So by default, miners order transactions based on how much transaction fees you are paying, right? But there's no consensus on that. The miners can also adopt like customized rules to order transactions. That's why miners has a dominating power in extracting BEV. And that's also why some people refer BEV as MEV. But we use the term BEV because it's more general, right? Anyone can extract. It's not just the miners. Okay, so as researchers, right, we are very interested in how much value has been actually extracted in the past and what's the security implication of the BEV in general. So we did an empirical study on how much BEV was extracted over a 32-month period. That's from December 2018 to August 2021. Our estimation shows roughly 0.5 billion USD was extracted on the Ethereum blockchain. So we are only measuring one single chain. The actual value extracted will be much higher than this value here. Our data set captures 11K unique addresses and 50K cryptocurrencies and 60K on-chain markets. One thing I want to emphasize here is initially we thought, okay, probably it's all right to just capture the big markets, right, with a lot of liquidity. It's okay to ignore the small markets. But our evaluation actually shows the small markets are very important. For example, the Dogecoin market actually contributed quite a lot to BEV. So it's really important to capture as many markets and as many cryptocurrencies as possible in order to get a holistic view of how much value was actually extracted. In the paper, we focused on 3 BEV sources, namely the arbitrage and liquidation, which I already mentioned, and also sandwich attacks. So arbitrage and liquidation are considered as benign BEV by many researchers. Sandwich attacks, on the other hand, is kind of malicious because the victim will be losing money because of sandwich attacks. There are many other BEV sources that we didn't capture. So the estimate we provided in the paper is really a lower bound on what is actually extracted. On this plot, we show how much was extracted by sandwich attacks. We found 174 million USD was extracted. So you can see on the plot, we only capture Uniswap, SushiSwap, and Banco AMMs. And over the period of 32 months, the profit growth from several hundred USD per month to almost 100 million USD per month by the end of 2021. So that's a huge growth, right? Like it's very, like it increased by several magnitudes. And you can see the profit is actually quite steady here, right? Like you can have like a similar profit for every single month. Here for the arbitrage, we see a similar story. It also started from several K USD and grew quickly to 100 million USD profit per month. However, for the liquidation, it's kind of different. We don't see steady revenue. So if you are an EV bot and you are extracting liquidation opportunities, then you don't get a steady revenue. That's because when the market is crashing, there will be much more liquidation opportunities. For example, here in the middle of like 2021, we see a huge spike where the market was actually crashing on that date. Okay, so that's what we measure, right? In the paper, we also came up with what I call alpha strategy, which is transaction replay attack. So this attack is really, really exciting, I find. It's a copycat strategy. So basically, the idea is you can observe some victim BEV extraction transaction on the P2P layer, and you find out what the victim is doing, and you copy the strategy, right? It's a copy trading. So the algorithm is relatively simple. It's only 3 lines of code, as I have shown on the slide. So given a victim transaction, I copy the sender, but I replace it with my own address. I copy the value, keep it as the same. And I also copy the input of the transaction, but I replace all the victim address with my own address. With only these 3 lines of code, right, I can quickly generate like 35 million USD over the 32 months period, just the 3 lines. So that's the alpha strategy I'm leaking in the conference, and I think it's still working as of today. Based on our evaluation, we found out that roughly 180K transactions are replayable. That's about 0.02% of the total number of transactions on Ethereum. Our algorithm is super simple. So it's a real-time algorithm. Like on average, we can replay a transaction under 0.2 seconds. Of course, you can scale it with many cores on many machines, which becomes like very fast. What's also interesting here is, as you guys can see, I have like a huge spike here in October 2020. So this spike is actually one of the attacks. It's the Emily finance attack. So we can successfully replay one of the attacks with this simple algorithm. What that means is we can actually have an intrusion prevention system. Like we can detect attacks on the network layer, try to replay the attack with our own address, and act as a white hacker. Okay. So the last thing I want to talk about is BEV forking and chain reorganization risks. So imagine here we have a blind miner, and the miner extracts a BEV in block A1. Now the attacker comes. The adversarial miner have 2 options. It can either extend the honest chain, basically he works on block A2, or instead, the attacker can fork the blockchain and try to steal the BEV into block B1. So if the attacker is successful, he mines B1 and B2, and this forked chain will overwrite the honest chain. Therefore, the attacker successfully steals the BEV from the benign miners. In order to understand the risks, we did some simulation and analysis in our paper using MDP. We found out that given a miner with only 10% of hashing power, it's rational for the miner to fork the blockchain if the BEV is 4 times the average block reward. So that's the high-level idea. But guess what's the highest BEV we found in the historical data? It's 874 times the block reward. That means in this case, even the smallest miner will try to fork the blockchain. And it's a horrible situation for DeFi. Okay, here comes my summary. So in this talk, we walked through 3 types of BEV sources, namely the sandwich attacks, the arbitrage, and the liquidation. We found out that roughly 0.5 billion was extracted in the past. We also walked through a new type of attack, which we named as replay attack. And if this attack was deployed in the past, we found out that roughly 35 million USD can be potentially extracted. And this replay mechanism can also be served as an intrusion prevention system. And please allow me to shamelessly do a plug about this DeFi MOOC, where we have fantastic instructors and guest speakers discussing about DeFi open opportunities and challenges. The course actually started this week, so if you are interested, please register. This work is partially supported by Chainlink Labs and Lucerne University of Applied Science and Arts in Switzerland. Thank you.
Thank you very much, Lee. Questions?
Hi, I just have like a definition question. So basically, I think there is two definitions of MEV, and the other one is called maximal extractable value, right? So is it the same as the term you mentioned, the BEV?
Okay, so there are multiple definitions. There is the extractable, which is measuring like what can be extracted, right? And I think the maximum extractable is kind of similar to extractable because like it's basically what can be extracted. There's also the extracted, which is what this paper is studying, right? Like it's studying like what has been extracted in the past. And whether to use blockchain or miner, right? BEV or MEV, that's like a kind of an open question. In my opinion, BEV is much more general comparing to MEV because there are so many entities, right, to extract values. It's not just the miners. So I prefer BEV in general.
But yeah, you know, in another the maximal extractable value, there's no miner in this term. But anyway, I'm very interested in the previous thing that the blockchain extracted the value, right? So, so what you study is like a past history. Okay.
Yep.
That makes sense. Okay, thanks.
Thank you.
Hello.
Hello.
So in 2016, Carlson et al. In CCS, they published this paper on instability of Bitcoin under the diminishing rewards. And there they compared what happens as you reduce block rewards when fees are increased in the future. Is this similar to the attack you're describing here, but with MEV replacing fees essentially, or treating MEV as potential fees, encouraging miners to reorg for that purpose?
I need to read the paper again in order to answer that question. But from my current understanding, what's different here in DeFi is the reward is not very stable. So you can see very high reward for certain blocks and very low rewards for other blocks. In Bitcoin, I think the rewards are relatively stable. So if you reduce the block reward, I don't think it's gonna have a big impact on the kind of the stability of rewards. Does that answer your question, or?
Yeah, what they studied there is the fees, so transaction fees. I guess you're saying transaction fees are relatively stable as compared to MEV?
Yeah, that's also my understanding. So in Ethereum, we also have transaction fees. But MEV for certain blocks, right? Think about arbitrage, right? Maybe a dummy like a trader made a mistake and he pumped the price like really high in one exchange. And maybe you can extract, I don't know, 1,000 Ether in a single transaction, which is much higher than the block reward and the transaction fees.
Thank you.
No worries.
I was wondering if you can talk a little bit how you measured the actual numbers for like how much BEV there was. Like, how do you compare or find out like this was just benign transactions and they weren't very well ordered to like how they could be ordered for like maximally profitable outcomes?
Yeah, thanks for the question. So in this paper, we applied heuristics to classify each of the BEV sources. Heuristics are not perfect, right? Sometimes we have like false positives and false negatives. So these numbers are only estimates on what's actually extracted. Of course, there are more generalized algorithms, so you can have like more complex rules to cap like a general BEV detection algorithm to figure out which account has made money in given like a random transaction. But we find that generalized classification to be even more kind of misleading because there will be higher false negatives and positives in that algorithm. So we fall back to the heuristics, and we only focus on 3 types of BEV to have a more accurate number.
Right, and can you just give like one example, like a heuristic that you use?
Yep, sure. So for example, for arbitrage, right, we detect trade passes, right? So we find if we can find a cycle trading from X to Y and Y to Z and Z back to X, right? If there's a cycle, we also check like what's the input amount and the output amount. So the output amount of the previous hop needs to be equal to the input amount of the next hop. In a sense that we are really strict on the rules on how we define the heuristics to minimize the false positives. But the details are all shown in the paper. So if you are interested, please read our paper. Thank you.
Thank you.
Yeah, go ahead.
Got it. So for the replay attack, I'm understanding that you can only decide if it's profitable to copy after the atomic transaction. So how can you ensure after an atomic transaction it's still operating as what you plan, or do you most of the time have to use a flash loan to kind of chip that atomic transaction with the one you're trying to copy?
Okay, so that's a very good question. So firstly, I want to say that the algorithm only works for atomic transactions. Yeah, right. So if it's non-atomic, it doesn't work. So non-atomic means like maybe sandwich attacks, right? You need to front run the victim and you also want to back run the victim. And now the replay strategy doesn't work because it's like 2 transactions. For atomic transactions, so it really depends on the victim, right? So if the victim is using a flash loan, I will also copy the strategy to also use a flash loan. Although maybe using a flash loan is not optimal, right? And there are also certain cases. For example, maybe the victim like needs 100 Ether to perform a BEV extraction, but I only have 10 Ether. Then in this case, I will fail, right? Because I don't have sufficient fund. So what we are doing is really we copy the transaction and then we simulate on past blockchain states in order to figure out whether it's successful or not. So that's what we do.
Got it. Thank you.
Thank you for the talk. Thinking about the future, how do you see the situation changing from moving to proof of stake?
Right. Thanks a lot. So that's a very interesting question. I have also thought about that quite a lot, but it's not trivial at this stage. So there's an ongoing discussion about PBS, so proposer builder separation, right? So I think if you look at a single builder, the game is not gonna change too much. But because there are like multiple builders at the moment, now it's relatively challenging for the arbitragers or for the BEV extractors to communicate with all the builders simultaneously. Like there's a higher network requirement. Also, I think for certain market manipulation techniques, for example, if you want to censor some transactions, it will become much harder now because you have like multiple builders and they are all proposing to like, the same miner can work with multiple builders, right? And if one of the builders is not censoring the transaction can still go through. But we need to do like a deeper analysis into this before I can like give very scientific feedback on that.
Hi.
Hi.
In your paper, I noticed you mentioned backrunning transactions a few times.
Yep.
And I'm curious about your predictions about the participation of crypto wallet companies in backrunning transactions.
Do you mind to elaborate your question a bit?
Yeah, so a lot of crypto wallets, they're kind of like the medium that transactions go through. And so it would make sense that they have a lot of data about transactions, and they can potentially backrun transactions because they are where transactions go through. What are your thoughts on that?
Okay, cool. So that's a very interesting question. So although we call DeFi like a decentralized finance, there are still many centralized components in DeFi. For example, Flashbots is not yet fully decentralized. But what we can do is to increase the transparency of this process. So, so yes, there will be wallets backrunning victims, but maybe these activities can be found by some detection tools. And once we found these malicious behaviors, we can reach some sort of consensus that we stop using this wallet. I don't see any better solution at this moment because I don't see trivial ways to kind of remove all the centralized component at this stage in DeFi.
Thank you for your talk. My question is about the trend of BEV and the portion of that versus overall value on the blockchain. What do you think would be a good measure of seeing how much of that is captured and how that will translate into future outlook?
I don't have a clear answer at the moment. Maybe we can bring it afterwards. We can have a discussion on that later.
Okay.
If you don't mind.
Yeah, thanks.
Sorry about that.
Any more questions? So I have also a question. So you mentioned that BEV attacks are attacks against security of the blockchain as well at the consensus level. So, and you mentioned that showed that there's a possibility of forking the blockchain. Would that be it's sort of a double spending attack against consensus, or just forking because the miner or the blockchain entity that does the attack will be incentivized to grow a different fork? And can you explain that a little bit more, if that would cause like double spending attack, or it's just going to be sort of unfair to other forks that have been legitimately growing?
Right. So that's a great question. Thanks, Marty. So in the paper, we actually only looked at forking risks, but there are many other consensus attacks or even network attacks which can be combined with this BEV incentive of forking, right? So if this is like causing all the miners to fork, I think the risk for double spending will increase dramatically because of that, right? Because every miner is working on their own fork, and then we don't know like what's going on anymore. However, I don't have like a quantitative result at the moment. I need to do my research, do more simulations in order to understand the risk of combining multiple attacks under like BEV forking situations.
That makes a lot of sense. All right, if there's no more questions, let's thank the speaker. So our next talk, again, is not about the future of blockchains. It actually tries to slow things down on the blockchain to achieve security and fairness in blockchain. Please allow me to welcome Pratush Tiwari from Johns Hopkins University to present his talk about an invertible VDF for Ethereum 2.0. The stage is yours.
Thanks. Okay, let's see. Yeah, no, that's not going to work. Is this PowerPoint? It's Keynote. It's fine. I can just... I think it's fine. It should be good. Thank you. Hi, everyone. I'm Pratush. I'm a PhD student at Johns Hopkins University. And today I'll be talking about invertible VDF construction that we have for Ethereum 2.0. And this talk is about a supposedly slow function, but hopefully it won't be a slow and boring talk. OK, so this is the talk outline. We'll be talking about what is the problem that we're trying to solve here, and how do VDFs actually help us like solve this particular problem, what design we have, what are the potential attack strategies, and how does this thing perform in the real world. So a lot of exciting things happening in the next few weeks. And one of the most exciting ones is the merge is coming. So once Ethereum switches to proof of stake, we will be doing things which are better for the Earth, and we will be consuming 99.95% less energy than we consume right now, which is something to celebrate. But this will bring some new challenges. So what are these challenges that I talk about, right? So Ethereum 2.0 has something called the beacon chain, which is there is a small group of validators, and they progressively build the chain of randomness, right? And we want to generate a single value per epoch, where we define epoch to be some amount of time. And then this generated value actually decides who the validator would be, right? And we have to come up with a protocol which honors this particular thing, that ideally you want to be, you want a particular source of unbiased randomness, and the goal is that the probability of any validator to be selected should be proportional to their stake, right? And this is something that a lot of people would want to do. They would want to be a validator, and hence there is an incentive to bias the randomness, right? Because you get to, let's say, produce the next block, right? So to motivate why we need VDFs, let's look at a first attempt which uses a RANDAO commit reveal scheme, right? And so each of the parties participating in this protocol, they have 32 bytes of local entropy, and they commit to it, and they publish this commitment publicly, right? And we assume that the honest parties, they keep their entropy private until their turn arrives. But as you see here, the key issue is who goes when, right? Because this has to be somewhat decided at random, right? So let's look at one simple approach using the commit reveal scheme that we talked about. So we have these different parties, and the value you see in red here below the validators is the value that they're supposed to keep private. So BR, B1, B2, up to BK, these values are supposed to be private until these parties are called upon, right? However, the commitment to these values are public, so that whenever, let's say, someone's turn comes up and they reveal their randomness, everything is good, and you can check that this person actually did well, right? So how do we start this protocol? So let's say we get a hold of, we do some ceremony or something like that to get some starting value which decides the first person, right? So this first person will reveal their randomness. Let's say it's the rth person, so you get BR, and that starts like a particular chain of randomness, right? And then using BR, you compute some small function of it which tells you who the next person will be, right? And that gives you BR1, and you XOR their randomness with the previous round, and you get the next round of randomness, right? And so even in this small chain, you can see the person who goes in the end, they have a strong ability to bias the randomness of the output. Let's say this chain ends at R3. What happens here is that the third person who goes in, if they see a particular bit, and let's say the particular bit decides an important outcome for them, then, and they don't like that bit, they can choose to not reveal their randomness. They can just go offline. You can have some negative incentive around it, but basically now they've biased the randomness. So for a particular bit, let's say, if they reveal their randomness and the bit would have been 0, then the bit should have been 0 with 100% probability, but now they don't go, and so the bit is 0 with only 50% probability, and they have a very clear ability to bias, right? So how do we prevent this? How do we make sure that someone who's going in the end, them choosing to reveal or not reveal is not something that they know will benefit them, right? So we want to take this biasability away. So what we propose is we use VDFs instead. So instead of us XORing the randomness of the selected person, what we do is we compute a really slow function on it. And what is the goal here? Once you compute a slow function on this person's output, what happens is, let's say it's my turn, I go ahead, I have to reveal my randomness, but the final output, R3, is a VDF. So at the time I reveal my randomness, I have no idea whether the calculated function on it will give me something that is favorable to me. So since I don't know in advance whether this thing is favorable to me, there's no real incentive for me to hide it. There's also negative incentive if I don't go, and hence most people would be compelled to just reveal it, their actual value here, right? So why do VDFs provide us these guarantees? Let's look at some VDF properties, right? So this is how you actually just compute the VDF. The next round output computes a function of the previous round, which gives you the next person who goes. And then you evaluate the VDF on it, and you get the next round's randomness, right? And as I said, the parties cannot know before the reveal step if revealing the randomness actually favors them. So yeah, VDF properties. So a VDF somewhat, it starts with like a setup. You generate some public parameters. And once you generate the public parameters, you have this evaluation function. This evaluation function is supposed to be particularly slow, right? So you have a certain input that goes in, and you get this output y. And it takes, as you see, the small snail there. It is a slow function to evaluate. And then you also get this proof pi. And then you have a verify algorithm. So what happens is once you have the input, the output, and the proof, if everything looks good, the verify algorithm verifies this as correct, right? So this is how generally VDFs were described in most of the papers. One interesting thing also here to observe here that is the evaluation process and the proving process, you can split both of them, and you can do them sort of in parallel, right? So you can have evaluation, which is a slow process, and it takes an input and evaluates an output slowly. However, to make a proof for this, that this is correct, it's not the same algorithm. And the proving can actually happen fast, and that's not a problem at all. And you can do both of these things in parallel. So what are the generic properties? So we have correctness, that if the honestly generated public parameter is used and things are honestly evaluated, the input, output, and proof will be accepted, right? And then you also have soundness, which is a common property that an adversary cannot get the verifier to accept an incorrect VDF solution. And then we also have sequentiality, which is an important property here. What it says is that even if you have an adversary that is massively parallel polynomially, then even that adversary cannot solve the VDF in sequential time, which is much faster than what we want them to solve them in, right? And then there are also some other VDF properties which are very important to us here. So we want tight latency bounds, which means that we will make some hardware, and let's say there is an adversary which is very powerful, then that adversary should not be able to have their specific hardware which solves it significantly faster than we want them to. The minimum hardware requirement says that since the process that is used, the VDF solving doesn't give someone a huge benefit, a monetary benefit, the hardware required for it should be cheap and easily available. You need succinct proofs for VDFs. This is to ensure that this huge, if the proof is huge, this doesn't actually expose you to a huge surface of attack. And quantum upgrade is also important in the future. It would be nice that if good quantum computers exist and we have some new attacks, we should be able to make minimal changes to the existing construction and still be able to use the VDF. Finally, we also target delay granularity. Delay granularity is, our target here is 1 second. So what does that mean? That means that if I give you a VDF, which I want you to solve in 10 seconds, I can also give you a VDF that you can solve in 11 seconds and 12 seconds, 13 seconds, and so on, right? So let's look at how we came about to this particular construction, right? So in 2018, Bonnet, Bonneau, Buenz, and Fish proposed a VDF which sequentially hashes an initial seed many, many times. And then you prove this result using a snark, right? So think back to 2018, ZK snarks were not as big a thing as they are now. So this was a bottleneck. We didn't have very fast implementations. And so in the beginning, the Ethereum Foundation had many initial efforts to focus instead on RSA-based VDFs by Piatchak and Veselowski, which are really brilliant mathematical constructions. They're very elegant, very simple. However, it was hard to set up a trusted RSA modulus, right? And then there were some hardware implementation issues as well, right? And then fast forward to the current time, ZKP technology has improved at a very fast rate due to many motivations and use cases. So the first construction, the first sort of approach where you have an initial seed and you perform a same function on it many times, and then you do some sort of proving, this is actually an approach which we take now because proofs are good, and so we can proceed with this, right? So the approach here is that we have this small function f, which is min root up here on the screen, and we use it many, many times, right? And so there are many different options for this function. So you can have, there's something called slots ++, and we do, but we choose this construction because this has one special property. So this cube root that you see on your screen, this can be computed using one single, not one single exponentiation, but one exponentiation helps you calculate this. And we do and slots ++ used, I think, 2 or 3 exponentiations. So that is one of the things. And the other thing is the structure here is very similar to the MIMC symmetric function, but we'll talk about this more. But the key idea is that this is a function that we know how to evaluate, and we know many things about it, and it's similar to other things that have been around, so it's not very novel or unknown, right? So how does it work? Well, someone evaluates a bunch of these chunks, so that this is one single sort of min root, right? And you have many min root evaluations stacked together. So as we'll see later, we can do like up to 2 to the 25 or something min root evaluations in 1 minute, but you have a bunch of these evaluations, and then we also do the proving. So we chunk them into smaller pieces, and let's say, for example, we take 2 to the 8 min root evaluations, so we make one proof for it, and then we make these proof chunks, and then we aggregate them together, right? And there are many good proof aggregation schemes that we can use for this, and I'll talk about this in a bit. But this is the general structure here, right? We have a function. We stack it many, many times for granularity and delay. The number of stacks basically gives you a difficulty level for the VDF. And then we do many proofs for smaller chunks, and then we combine it to a single proof for the whole thing, right? So, but yeah, so we didn't talk about security at all. And since here security, like proving things is hard about that function, similar to how a lot of symmetric cryptography works. We can say a lot of things about the proving system, but comparatively little provable guarantees about the smaller function, right? So how do we think of security? So there are a few key attack strategies that we need to think of, right? So the first is a sequentiality attack. So what does this mean? It's a very natural idea to see if I know that I will be computing VDFs, and knowing the VDF solution in advance will give me some benefit. So what I'm going to do is, before this whole process starts, I'm going to sit at home and I'm going to pre-compute a lot of this function to give me some sort of head start, right? And when I'm online, I hope that one of these instances actually shows up, right? But one direction is actually cheaper, so we need to ensure that the attack computes like some chains of inverses. So you have a bunch of these chains that you pre-compute in hopes of meeting them at a certain point. So we have some numbers in the paper which assume that, okay, like let's say you make a certain number of calls to the function before the whole thing starts, then you have this like certain probability of actually benefiting from it and meeting this pre-computed chain. I'll skip this for now. The other thing that you can use to attack is the algebraic structure, right? So this would be very devastating if we find something like this. So what if you found an algebraic property in this whole structure which lets you skip all of these evaluations? So it lets you shortcut the whole function so that you don't have to go one by one. And this would be disastrous, and someone could compute the VDF much faster than expected. So for you to speed up D rounds, you solve this particular equation, right? Which is a multivariate equation. And then if you have like an univariate equation of this form, then you can use the Grosvenor basis algorithm. The concrete efficiency of the Grosvenor basis algorithm is not is not particularly known. So it would be a really unlucky case, and the cube root of small d here would have to be really small for this to actually be a concern. So to the best of our knowledge, this is not something which is problematic for us. Then we also need good latency bounds, right? So what does this mean? This means that we need the fastest exponentiation algorithm, which we will be implementing in hardware. And for this, we use the windowing ladder algorithm, which most of you probably know about. So it splits the exponent into this window, and it pre-computes power of x for this window, and then simple square and multiply, right? And so the best known lower bounds for this process, we studied them. They're by Veselowski and Williams, and upper bound by Mart and others. Yeah, so these papers are on ePrint. And then another big elephant in the room is also quantum attacks, right? So what happens if there's a quantum computer? How do things go? Does everything break? Should we all go home? Well, not so fast. So the natural idea is that if you have, you're trying to pre-compute things, right? So you have these many chains that you pre-compute in hopes that you meet one of them, right? And the natural idea is that if you use fast quantum searching, you get a quadratic speedup, right? This is Grover's algorithm. And so you can find one of the targets faster, right? But it only gives you a quadratic speedup. And so for a 128-bit security parameter, we have 40 bits of loss, and similar loss for a 256-bit security parameter as well, right? The other thing is that the function I showed you, right, it's very similar to MIMC. MIMC is now a very popular symmetric key crypto primitive, which is being used for many reasons. One of them is like if you use it inside a snark, it's very fast to compute, right? And the security of MIMC is based on this particular assumption that the resulting polynomial has large algebraic degree, right? And this is not something that's very new. It has been studied to a certain degree in the last few years, and there has been public scrutiny. Namely, there's these two papers at AsiaCrypt at 2019 and 2020, and no counter-argument to this assumption has been found thus far, right? So it looks like we're possibly OK in this regard as well, right? So now let's talk about, we've talked about security, how does this thing work, but let's see what it does in the real world, like what have we done with it already, right? So in our hardware, in 1 minute, we can make 2 to the 25 calls to the small function that I showed you, minroot, right? And each minroot chunk requires these many constraints, and these many calls to the function f, and the proving happens over a GPU. This is not something that's unheard of, actually. Filecoin has Groth16 proofs which have similar size, and they have been successful in deploying them at scale, right? The key idea is that you have so many calls to this function f, but proving is extremely parallelizable. So as you compute your function f, you can also do your pre-proving. So your function is evaluated in hardware, your proving happens in the GPU, and they sort of finish at the same time, right? And that is the ideal thing. Proving might be a few seconds slower. As an example, if you do these 1 minute delay chunks, and let's say I have a VDF I give you, which is roughly, let's say it takes 3 days for you to solve. For me to aggregate all the smaller 1 minute proofs, it only takes 1 minute. So you compute your VDF in 3 days, and then the proof is computed in parallel with only 1 minute delay, which is pretty good, right? And so the proof systems that we actually implemented this for is Nova proofs, which is a recent construction. It was proposed by these great people. I think there's an implementation by Microsoft as well, and it gives us a great improvement over Groth16. It does not require any FFTs for proving, and the verifier circuit is constant sized. It's like the most optimal one we have. It only takes 2 group scalar multiplications. And we implemented this whole thing that I talked about over the pasta curves with the minroot function and the Nova proof system for proving and aggregation, right? And some hardware numbers here. So the ASIC will give you roughly 1 minroot takes 300 nanoseconds to evaluate. So you can do roughly 330 million minroot calculations within a second, right? And what's nice is that a single GPU will create a snark proof for 2 ASIC VDF evaluators. This is for a 384-bit curve. When we go to a 256-bit curve, this should double. So one GPU should be able to create snark proofs for 4 VDF ASIC evaluators. Yeah, that's all. Thanks a lot.
Thank you, Pratish. Questions?
Hello, very interesting construction. The same problem was faced in the design of Ouroboros, one of the first proof-of-stake blockchains published in 2016, the selective revealing problem. And the way they dealt with this was to introduce a PVSS, deal the secret in a way that is provable and associated with a commitment, and then require the honest majority to reveal if there is no reveal by the optimistic case of the party actually revealing. Okay. I guess the problem in Ethereum is that there's too many validators to do that, or why didn't you take this approach that seems a little bit more natural? I guess VDFs to me seems that we require this extra computation that we are trying to get away from in proof of work, right? Yeah. So why didn't you follow the PVSS approach?
Well, so one thing is that it is not similar to proof of work. I understand that it's extra computation. It's not as bad as proof of work by any degree, right? That's one thing. The other thing is, I'm not sure of the PVSS construction, but I don't know if it provides you a delay guarantee at all, right? Because if you, I mean, there might be other things that we need to take care of, which is the validator identity should not be, whoever selected next, their identity shouldn't be known too far in advance, right? I don't know if the PVSS construction allows you to.
The PVSS construction does not introduce a delay, but does not require a delay because it does away with the selective revealing problem. Because when I commit, I also secret share to the rest of the peers the secret. So if I go offline and select not to reveal, they can reveal my secret.
But they have to come together for that, right?
Yes.
Yeah, so that's the main
So it's
thing.
an online versus offline problem. Okay.
I have a follow-up comment on that. So I think in this setting, your networks are asynchronous, or they could be like, they're always assumed to be synchronous. Because I think the PVSS protocol for coin flipping, I'm not sure if that would work in asynchronous setting. We still might have, the last person can, take advantage of the delay in the network and, avoid voting or opening the vote. So that could be an issue also.
Right, so yeah, the synchronous part also, if that makes sense. And I also wanted to add one more thing, which is Chimed from Protocol Labs has implemented most of it. And I had a link up here, actually, if the people in the back could throw the slides back on. Yeah, so if people want to look at the code, they can go here. It's actually quite recent, so you might be able to look at the Nova proofs part as well. Yeah, I'll take the next question.
Thanks for your nice talk. So my question focuses again on this topic of how are we really avoiding proof of work here, and how is it different from proof of work?
Well, first of all, you don't need to buy millions of dollars of hardware, right? So that's one thing. And then the other thing is, since you don't need to buy millions of dollars of hardware, you don't need millions of dollars of electricity. And this whole thing, it seems like, oh, you're computing millions of functions, but it happens on a very small chip, and proving happens in a GPU. So it's much nicer than that.
Is there competition? Is there something that could end up being competed upon, so it would scale up considerably?
I mean, the point here is that proof of work has very clear rewards, right? So like if you produce the next block, then you get however many coins as a reward, right? Here, like solving the VDF faster doesn't give you a huge monetary benefit at all. It's more of a public good type thing. So there is very little incentive for people to invest millions of dollars to do something like that.
All right, thanks.
Yeah, sure.
Thank you very much for the talk. I wonder what's the minimum hardware requirements, and what's the difference with the stronger machine here?
I'll take this question offline, but yeah, the minimum hardware requirement is you have a small ASIC. It's not too big, but yeah, we can talk about this later. Yeah.
So as a reminder, please be mindful of the people in the line when you go to the line for asking questions. Yeah. No worries.
How do you compare this to using verifiable random functions for the selection of validators?
Right, so verifiable random functions are a great tool, and they also let you select validators randomly. The key thing which we have here, which is different from VRFs, is the delay part, where it takes some amount of time to actually know the output of the VDF. So let's say I'm supposed to go next. I don't know what the VDF output on my input would be at the time I reveal, right? So when I'm revealing, I don't know whether me revealing or not helps me at all or benefits me, right? And hence, I will not act in a bad way.
The VRF does not require the delay element because you cannot fake the output. If you get selected or not at random.
But I can still choose to not reveal, right, in a VRF? I mean, I can just go offline and not go at all, and then I'll bias the thing, yeah. Cool.
If there's no more question, one quick question also about the delay hardwares in general.
Yeah.
So there is dependence on the hardware architecture because the hardware is an ASIC, right?
Sure.
And so how is that we are dependent? You know, the VDF is dependent on where it is being used. Maybe I didn't get something because I had to run to find the next speaker, but can you elaborate a little bit more on that?
Okay, so the key idea here is that we have something where we want a lot of granularity, and granularity means granularity and also a bound on latency, right? So if you want both of these things, it's best to have application-specific hardware, and that's what an ASIC is, right? You have an application-specific hardware, and then you have a higher probability that no one will make something that is faster, right? So that is one part. The other part is we split the hardware and the proving aspect, right? So let's say there's a quantum computer in the future, then we can actually just replace the proving in the GPU, right? So that's just software. And so you change your proving system to like a Stark-based system or anything else which is post-quantum secure, but your proving hardware, your evaluation hardware is still useful. You can still evaluate the function with the same amount of granularity, but you can change proving to be post-quantum secure, and then you have a post-quantum VDF. So I hope like that helps.
Yeah, that makes a lot of sense.
Perfect.
Thank you so much. So let's thank the speaker one more time. Great work. Thanks. All right, so now that we initially looked at the past on the blockchain and slowed things down for VDF, for achieving security and fairness, it's time to make things fast and make things private so that nobody can look at the past and the future. So let's welcome Matthew Baudet from Linera to present his talk about the low-latency blockchain without a mempool.
Thank you. Thanks, Maddie, for the introduction. Cool. So does this thing work? Yes, it does. Awesome. So yeah, it's a pleasure to be here today. So as you know, as blockchain technologies are aiming for mass adoption, there's a growing need for decentralized applications that that stay responsive and reliable at internet scale. And at Linera, we're working exactly on that. So we've been working on a new decentralized multi-chain protocol dedicated to low latency and high throughput applications. And so my goal in this talk is to give you an overview of the protocol. In particular, I will present two key ingredients. I will discuss the two key ingredients in the talk. The first one is that in this system, each validator is designed to be to scale like a normal web application. And in particular, every validator has all the chains, all the shards, if you want. And the second key ingredient is that we encourage users to operate their own chains. So this is obviously useful for sharding. It's also useful for latency, as we'll see. In that case, it removes the need for a mempool. So obviously, using large, individually scalable validators is not common. It's not traditional. So let's say why we would like to go that route, and to do that, let's look at traditional systems, like a few of them at least. So let's start with a traditional blockchain. So scalability in traditional blockchain is like basically how fast you can create blocks and how large they can be, right? And so traditionally, this transaction rate has been a function of how good the consensus protocol is, and in particular, given the networking constraints in terms of delay of propagation and bandwidth in the network. Nowadays, I would say in modern designs, more often than not, it seems that what limits the transaction rate is really just the execution rate of user transactions in a single chain, right? And so here you can definitely go very far with very smart optimizations to, let's say, to use parallel execution. But my point is that if you aim at something that is arbitrarily scalable, there's only so much you can do. So for this reason, another system has been considered also in the past, which is just using many blockchains in parallel. And so in traditional blockchain sharding, every shard has a separate set of validators, which is nice. You got small validators, community hardware for validators. But the problem is now you need to explain how cross-chain communication is going to work in the system. And in fact, it turns out to be quite complex. There's quite an overhead when it comes to communicating, to sending messages between those individual blockchains. And in fact, this is so much true that after a while, adding blockchains is going to slow down the system in practice. So another very, very interesting design that is proposed nowadays when it comes to scaling blockchains in arbitrary way is to use validity rollups, to use ZK rollups. And so here, what we want to do, we add a second layer, a layer 2, and we want to use to gather lots of user transactions, compress them into this hopefully constant-sized validated proof. And now the layer 1 just has to seeing this short validated proof and just needs to verify it using the magic of ZK proofs. So now this is great. The only thing is that the cost of verifying this proof is going to be pretty high in the layer 1, the gas cost. So to make the whole thing work, you need pretty large blocks in layer 2. So I think it's fair to say this is never going to be really low latency, at least in the sense of this talk. If you want confirmation in layer 1. Okay, so in this talk, I'm interested in this new system where every validator runs every shard. Okay, and so we'll see that this is really nice for cross-chain messages because now they live in every single validator. Every validator looks like a Web 2 service, so you can scale them just like you do for a normal web application with a load balancer, a number of workers. You can add workers if needed. You can downscale if needed. And we also see that having many chains, you can try to put the user in the center of the protocol and improve block finality compared to traditional blockchain protocols. So I start with an overview of the protocol, and first with the security model. And so this is a fairly standard security model we're using that is common for blockchains based on BFT consensus protocols. So for the purpose of this talk, let's say there are 3 F+1 validators, and we consider that at most F can be malicious. So what's important here is the notion of quorum. If we have roughly two-thirds of the validators, 2 F+1, then you can aggregate their signature into what we call a certificate, and that's going to essentially prove that the block is final. In this system, we also we make assumptions on the maximum number of malicious validators, but we don't want to make any assumption on the network when it comes to safety. Sometimes you have to do assumptions on the network delays when it comes to liveness. We try to avoid that as well. All right, yeah. So how does the protocol work? So we have these n validators. Each of them has all the chains. And now let's say we have a user that user B that owns a chain, okay? And so that's the kind of the also distinctive feature of the protocol is that we want users to operate their own chain. So we're assuming we have some form of full node for the chain B. So it's sort of a partial full node on the client side. And the client is going to act as a leader, trying to propose a new block to extend the chain in every validator in parallel. And so the nice thing here is that since it's your own chain, you can just tell the validators what is your next block. So you just broadcast your block in parallel. You gather a number of signatures. And in the simplest case, not always, but in the simplest case, once you have the signature, all you need to do is to broadcast the block back. And that's basically it for the finality. So what's interesting here is that, and important for a design, is that validators don't talk to each other. The client is in the middle of the communication. So this is important because we want to let users have their own chain. And of course, users sometimes, they are not going to use it, right? And so when a chain is not in use, we don't want to pay operational costs of like gossiping or validators like having to talk about timeouts or this kind of overhead, right? We want just the validators to just forget about the chain entirely until it's used again. Okay, so next I'm going to explain the cross-chain messages, which is really the crux of the protocol. And in particular, so the originality is that, like I said, every validator has all the chains. So the cross-chain messages, what's happening is that it's just a single message inside each validator, right? But of course, what's interesting here is that those messages are asynchronous, and validators, they don't need to agree on the order. Actually, it's very likely that they are going to schedule the messages differently than their neighbor. So we need to talk about consistency in the system. Fortunately, the theory started a while ago with a protocol called FastPay. So FastPay in 2020 so I worked with, when I was at Facebook with George Danizis and Alberto Sonino. And it was very much like what I'm presenting today, but it was restricted to payments. And also, we didn't have the notion of chain. It was more like user account or account-oriented. And so in FastPay, so it's only about payments. So for every, now what I call a chain, you get a balance. And what you want is to be able to, so every account has an owner that has a signature on the account. And what you want is to be able to move the money around, okay? So to do that, you do this round-trip protocol that is described in the previous slide. And then there needs to be a cross-chain message that says, for instance, in here, from A to B, hey, B, you have $3. You have $3 or 3 Bitcoin. And so, of course, when you create a new block and you say, I want to move money out of my account, there's a balance check. So every validator only signs the new block if you're actually spending money that you have on your account, according to their local view of the chain. So what's interesting here, talking about consistency, is that there are cases where you have a new block, but your view is kind of lagging. You haven't seen the money coming in yet, but that's fine. You are still going to send the money away, which means the local balance of an account for a minority of validators can actually go negative temporarily. All right, so normally, yes, you would expect first B to receive the 3 and then to spend them, and it has to be the case for a quorum of validators. But then for the remaining ones, maybe they're lagging, maybe they haven't seen the message coming from A, and they see the block that is certified, and they're going to trust the quorum of signature on the block and actually send the money to ear X, okay? But later on, maybe the chain of A is going to be receiving the block that was missing, and then the message is going to be scheduled, and then the balance of B here, in this case, is going to go to 0 again, from -3. So so this is nice and well, but this is only for payments, right? And we want to do a multi-chain system with smart contracts, arbitrary user messages, and we've got this consistency problem. How are we going to do it? So the intuition here is is to give every chain, to give it an inbox where the messages are going to come and wait to be selected. And they are going to be selected in the next block proposed by the leader of that chain. And while we're at it, we're going to ask the leader to tell us in which order the messages needs to be, the incoming messages need to be executed, right? So of course, there's still going to be this very interesting phenomenon where sometimes a chain is seeing a block that is accepting a message that actually hasn't been received locally yet. But that's fine. That's only for a minority of validators. Everybody else, when they see a block, they verified, when they saw the block that was certified, if they signed for it, means they actually saw the message, right? So this is what I explained here. Block validation. This is the equivalent of checking the balance in FastPay. In FastPay, somebody wanted to move the money out. You had to verify you had the money. Here, somebody wants to propose a block that accepts a number of messages. Before you sign, you have to verify that those messages are actually in the inbox. But interestingly, sometimes you receive a block that talks about messages that you haven't received yet, okay, a certified block. And so in this case, you need to track that you have executed the message by anticipation, right? And you need to remember that so that when the message comes, you can say, look, okay, I executed that message before I had received it locally. Now I received the message locally. That's fine. I'm back to zero balance in FastPay. Okay. And importantly, when a new block comes in, so it's going to list some messages. But even if it doesn't, you really don't want to sign the block if you have pending messages that were already executed by anticipation and you haven't received. Okay, so if some messages are received for minority validators, you're going to have to wait for them to arrive before signing a new block. Why is it important? So first, why does it solve the problem of consistency? So now we can see that the set of messages that are scheduled in the system or waiting to be received or already received is just a deterministic function of the heights at every block, in every chain, right? So if two validators, to put it differently, if two validators have the same height for every block, and we stop creating blocks, eventually they will have the same state for the inboxes for all their chains, right? Next, in terms of safety, I explained, like I said, so when an honest validator signs up for a block, needs to verify that all the messages are there. And so in terms of safety, we have this property that if a single honest, so if you see a block that lists some message you haven't seen, there's a quorum that signed this block. And in this quorum of signatures, of course, there's one honest validator. There's F plus one of them, normally. And you know that person vouched that the messages are going to arrive later. So that's why it's safe to execute a block that even if some messages are temporarily missing, because you know one honest node, at least one honest validator has seen them. And in fact, as a client, sometimes your work is to update the lagging validators and to forward them the blocks that they might be missing, right? So you're receiving a message, as you see that the chain of B receiving a message. Some validators haven't seen the corresponding block in A's chain that was sending the message, so you need to actually forward the block that was missing, A's block that was missing in some of the chains. And so the system needs to make that easy. But once you do that, you have this property that you can, as a client, you can always give to the validators what they're missing so that you can make progress on your own chain. All right, lots of time. So now I can talk about a few applications that are using this system. I picked some applications that are playing the strength or showing like the flexibility of this new framework. And so the first application I wanted to discuss with you is like for fun. It's just imagine you want to play a game of chess on a chain. So what's going to happen is you start with a chain from the tournament, and it's going to send a message to create a new temporary chain where the game of chess is going to be played between A and B. Maybe there's also a referee in the system. What's interesting here is that because the chain is dedicated to this game between A and B, we can teach the consensus protocol whose turn it is during the game. And we can try to simplify the consensus protocol and remove some parts that would be otherwise needed. For instance, the leader election or the mempool. And although this chain is shared between several people, we can still try to avoid a full consensus protocol. And of course, you may have to do some trade-offs with liveness. So for instance, in this case, if A and B stop proposing blocks, some stop correcting, so actually one of them, it was his turn, they will time out, they will go to 0. Maybe we need to trust that the referee will, in that case, will come in and will add a block that says, okay, the player A lost. In that case, that would send a message back to the tournament chain that would terminate the chain, and that would work just as well. Cool. And another application is slightly more complicated, but not much more complicated, is the atomic swaps. And so here, imagine you have 2 users and they want to trade, let's say, BTC for ETH. I mean, wrapped BTC for wrapped ETH in the system. So one of them has to send a message to the system to set up a temporary chain that is going to contain an escrow smart contract. And now the 2 users, they actually have to send their asset to the escrow smart contract in this temporary chain. And when that's the case, either of them, one of the 2 users can create a new block in this temporary chain to confirm the swap that would send back messages that contain the assets with switched owners. Of course, we want the system to be safe, and any user can stop collaborating at any time. So we want also another command to be available, which is going to cancel everything and just send back whatever assets were locked into the temporary chain. We want to send them back to their original owner. And so once again here, in this case, if we want to avoid a full consensus protocol for the temporary chain, we can make some trade-offs with liveness. And in this case, actually, there's only a very small trick that we can do, is we can say, look, this temporary chain might receive blocks from either user 1 or 2, right? But we are not going to allow a user to propose a block until they have actually escrowed, they have actually locked their asset in the chain. So once again, we see that we can use the application logic of a temporary chain to improve the consensus protocol. So why is that interesting? So it means that if I set up a swap and the other user never locks their asset, I'm the only leader on that chain, so I can very quickly, whenever I want, I can cancel. It's going to be deterministic, and I get back my asset. The only trade-off here is that if the 2 users have locked their asset into the temporary chain, and if we decide to use a simplified consensus protocol without leader election, then the 2 users could, although they have locked their asset, they could sort of talk and propose contradicting outcomes. So it will fail the block proposal. And they could do that. And if they continuously try to propose different outcomes for all the rounds of the protocol, then there will be a live lock situation. But that requires the 2 users to actually want to lock their assets forever and actually actively DOS themselves forever, which we could argue is not realistic. And in fact allows us, so if we believe that allows us to remove leader election in the protocol and have this very nice atomic swap with low latency and a very simplified protocol. All right, so I guess that's it. So today I was giving you an overview of the linear wrap protocol, which is a new kind of decentralized protocol where validators are internally sharded. So that means that they can kind of individually scale when needed, adding workers to deal with more shards. Sorry, to deal with the chains. I also explained how users can be put in the middle of the system and manage their own chain, and also how we can create temporary chains with some application knowledge and tweak the consensus protocol to achieve a lower latency than a traditional blockchain with a full mempool and leader election and so on. And also I explained how we generalized the cross-chain messages initially in fast pages for payment and made them strong enough to support any kind of smart contracts and arbitrary user messages. Yeah, so this was an overview. Obviously, this is the beginning of a new direction, I think. And there's a lot of things I didn't mention in this talk that we are actively working. Some things such as reconfigurations, proof of stake, auditors. I'm happy to comment on that. And other than that, I can just say we're hiring, and that's it. Thank you.
Thank you, Matthew. So we can take one question from there.
Thank you for the talk. Really interesting direction. I had a question. So I'm confused about, in some sense, what's being proposed. It seems like you're proposing at first to use Byzantine consistent broadcast to do payments. Is my understanding correct so far?
Yeah, so yeah, I should have probably pronounced the word consensus broadcast. Thanks for bringing this up. So it's definitely the center of the original motivation with the FastPay paper. But I think there's something that's emerging as we are developing the protocol is that it doesn't really matter how you extend chains, and you can actually make that very flexible. So for some power users, you could provide them with this very simple one round trip protocol, which is called reliable broadcast. But if you want more power, in some cases you need 2 round trips. And then for some chains, you may need also like a full consensus protocol. So it really depends on the kind of chains that you are creating in the system or configuring on the fly in the system.
I see. So it's not just a BCB-only system. At some point, Byzantine agreement is involved, and
yeah.
Okay,
And in fact, even for a single user chain, for some properties that would depend on external oracles, the single round trip protocol is not enough anymore, and you need 2 round trips.
I'm wondering if you've thought about state transfer and state synchronization in the BCB variant of your design. So, because there the replicas don't really agree on the state. Each replica has a different view of the state, right? And when a replica goes down, it seems a bit tricky to potentially recover.
So I think in this new formalism where we talk about chains instead of user accounts, it's more classical what happens in terms of synchronization. Like the client has a full node and it's just uploading the last part of chains that might be missing in some validators when needed. So I think that part is actually becoming more like normal system of chains. Yeah, the only thing is that when you receive a message, you need to track the state of the sender and how, like the height and all the blocks that that are needed, causally speaking, to create that message, so that you may update lagging validators, so that they also send you the message in their view. Does that make sense? Thanks. Mm-hmm.
Thank you, Leo.
So. My question is regarding the protocol design. I think you haven't talked about the decentralization. So running the node for one chain is already very demanding. So your validator will run the node for multiple chains. So from engineering perspective, it's already gonna put a lot of requirement on the hardware to run the node. So eventually, if a validator can only have to become a very super node in order to support multiple chains. So that will reduce the decentralization of the protocol. What are you thinking on this?
Right. Yeah. I mean, so we're definitely assuming that each validator is scaling, potentially arbitrarily, and so either they have data centers or they're using a cloud provider. I think nowadays lots of validators are actually using cloud providers already. Now, in terms of decentralization, of course, we want to make it easy to deploy on any kind of cloud providers out there. So like if there are 10 of them, and also eventually maybe the community is going to provide validators that are blockchain friendly and sort of decentralize themselves. That's, yeah, but I think that's, talking about decentralization, I think something that's interesting also is as how can you audit the system? Because, and that's something we really have in mind here, to make sure that individual collaborators, I mean individual nodes with just commodity hardware can audit at least a portion of the system, and that collectively the community can always audit all of the system continuously.
Okay. Thank you. Question from there. You can go from that side.
Okay, so it seems to me that the user is going to be responsible for choosing how strong a level of synchronization they want. And so maybe if I'm a naive user, I'm going to say, well, I'm always going to choose the one round-trip protocol. It's going to be fast, but then my application invariants are going to break, and it's going to I'm not going to understand what's going on. So how do you plan to support users?
Right.
So,
Okay.
Is this problem real? And if so, how do you plan to support users?
Right. So here, it's all about liveness, obviously, right? It's not about safety, right? So as a user, if you use the one-trip protocol and you use it wrong, you may block your chain. So probably for normal users, we will just make it the default to use the two-round-trip protocol where this never happens. And then for power users that want really to scrape like every bit of latency they can, then they will be able to use a single round-trip protocol. But that will come with a number of responsibilities. Yeah, they may definitely. I mean, for the single round-trip protocol, and this is well known. I mean, you can definitely, if you start just sending contradictory blocks to validators, you will go into a state where the chain is blocked. Yeah. There's no view change in the single round-trip protocol. But it's very easy to have a two round-trip that, so you're doubling the communication, and then you have view changes, and you're back to a place where you can always recover from problems.
Okay, thanks.
So we can take one more question only.
Okay, so the lack of a mempool means that the transaction ordering is first come, first served, correct?
Sorry, say that again?
The lack of ordering means that transactions are essentially first come, first served, right? So if I send my transaction in first, it's first of the block, right?
So in your own chain, there's no negotiation. You're just telling this is the next block. Yeah. And you're not, thanks to sharding, that should not really depend on what other chains are doing in the rest of the system.
Gotcha. So how do you avoid issues like DDoS attacks? Like I think we've seen with Solana, the lack of the mempool essentially means that there's like a lot of spamming issues. Right.
So I think we are actually in a better place here to charge fees upfront whenever a user is talking to validator. We could. This is still obviously up for discussion in the system, but I mean the roots of the system is a fast payment system, right? So we are really in a good place if we want to charge users. We could even charge users for a fee that depend on which validator you're talking to. So there's a lot of room actually here for protecting us against DOS attacks. I think it's easier to protect that kind of system than securing a mempool.
Okay, gotcha. So kind of distilling it, like because it's more like these simple transactions, it's more resistant to it, and also you can have like hotspot style markets where like people are just targeting like one individual validator, then it's kind of like they face increased fees, correct?
Well, I mean, the short answer was like you can make it so that just talking to validator is always costing you something.
Okay, gotcha.
So yeah.
Thank you.
So let's thank the speaker one more time. Thank you, Mathieu. So this concludes the second to last session, Future of Blockchains. We'll continue with the last session at 2 p.m. And we can have lunch now. Thank you.